Hello friends and welcome to In 5 Minutes. Today we are going to learn to make the layout of a NAND gate. We'll follow the 4 steps that we used to follow for other layouts as well. First, we'll make the symbol. Next, we'll make the Cmos implementation of NAND gate. From that Cmos implementation, we'll make the stick diagram, and finally we'll make the layout from the stick diagram. The stick diagram is the most important step as it will give us an insight as to how our final layout will look and also the spacings between the different interconnects. So let us start by making the NAND gate symbol. It has 2 inputs A and B and 1 output Y. Next, we'll make the Cmos implementation. In Cmos implementation for a NAND gate, we know that the PMOS should be in parallel while the NMOS should be in series. So first we'll make the VDD, then the parallel PMOS, followed by series NMOS. Make sure that the NMOS are facing in the opposite direction. This would help in making the connections better. And lastly, we have the ground. Now let us connect the PMOS and the NMOS respectively. The first connection is your input A and the second connection is your input B. And this is your output Y. Now let us name the NMOS as N1 and N2 while the PMOS as P1 and P2. Next, we'll make the stick diagram. So first, I'll draw the N diffusion layer line. Next, I'll draw the P diffusion layer. An interesting point to note here is that the NAND gate is just an inverted version of the NOR gate when you look at the stick diagram. We'll draw the 2 polysilicon layers to represent the inputs A and B. Now, I'll draw the VDD line and the ground line. Let me connect the ground to the N diffusion layer. The cross here represents a contact which has to be drawn with black color. Now I'll connect the VDD to the P diffusion layer at 2 points. Here again we'll make the contacts with black pen. Finally, I'll draw the contacts which will give us the output Y. I'll also draw the N well around the P diffusion layer. The N well is represented by a dotted line shown in green color. Now let us label our stick diagram. First is the ground, next is the VDD, next are your inputs A and B, this is your output Y. The polysilicon acts as this line here. When the polysilicon crosses over the N diffusion layer, it creates an NMOS, while crossing over the P diffusion layer, it creates a PMOS. Next is your N well. Now we'll see the spacing between the different interconnects. The metal will extend beyond the contact at 1 lambda, the contact itself of 2 lambda, the distance between the contact and the polysilicon being 3 lambda, the polysilicon length being 2 lambda, again 3 lambda, and we'll follow the calculations forward. This totally will be 24 lambda in length. Now let's see the length of the polysilicon. It should extend 1 lambda beyond the diffusion layer, the diffusion layer itself being 3 lambda. Now while calculating the next distance, we'll have to take into consideration the metal-metal distance, which is 3 lambda, then 6 lambda between the p diffusion layer and the n well, the p diffusion layer itself being 3 lambda, and then 1 lambda beyond the p diffusion layer. This in total is 20 lambda. Calculating the distance of the end diffusion will take into consideration that the contact distance between the silicon and the metal contact is 3 lambda, the contact itself of 2 lambda, and the metal beyond the contact should be extended to 1 lambda. This gives us a distance of 6 lambda from the polysilicon for the end diffusion layer. Similarly, for the other side of the end diffusion layer. Now let us make the layout. First, I'll draw the p diffusion layer of 24 lambda length.